Hello everyone and welcome back to Introduction to Number Theory. In this video, I would like to consider several examples of how ideas related to Euclidean algorithm and linear representation of the greatest common divisor could be useful in different situations. For instance, consider a fraction 2n plus 3 over 5n minus 1. Well, n is an integer. Is it reducible? I don't know it. It may depend on n. So let's try and put certain values of n into this fraction and see whether it will be reducible or not. For instance, if n is equal to 1, then we have 5 over 4. Well, it's irreducible. If n is equal to 2, then we have 7 over 9. Well, also irreducible. If n is equal to 3, then we have 9 over 14, also irreducible. If n is equal to 4, then 11 over 19, irreducible. By this time it seems that it will always be irreducible, but let's continue. If n is equal to 5, then it is 13 over 24, and if n is equal to 6, then the fraction will be equal to 15 over 29. Well, the enumerator increases by 2 every time, and the denominator increases by 5. And if n is equal to 7 now, then the enumerator will be equal to 17, and the denominator will be equal to 34. And we finally found a reducible fraction of this form. We could continue this, but we understand that there are infinitely many values of n, so we need to think up with something more general than just checking different values of n. So we see that sometimes this fraction is reducible. Let's try to figure out, well, if it is reducible, which means that both enumerator and the denominator have a common divisor greater than 1, what integer could be this common divisor of denominator and enumerator? In other words, what could the greatest common divisor of 2n plus 3 and 5n minus 1 be equal to? Well, we see that it can be equal to 1. We see that it can be equal to 17. But what are these all possible values of the greatest common divisor? And here we will use the idea of linear representation of GCD and try to eliminate n by multiplying the enumerator and the denominator by some integers. Well, if we wish to eliminate n, then we could put 5 over here and minus 2 over here. This will give us, well, 2n multiplied by 5 is 10n, and 5n multiplied by 2 is also 10n, and they kill each other, and 15 and plus 2 gives us precisely 17. So we see that there are integers 5 and minus 2 such that linear combination of enumerator and denominator is equal to 17. This means that if the fraction is reducible, then it can be reducible only by 17. Because if both 2n plus 3 and 5n minus 1 are divisible by some d, then 17 must be divisible by the same d. Therefore, only 1 and 17 could be the greatest common divisor of a numerator and denominator. Thus, if the fraction is reducible, it is reducible by 17 and nothing else. Another example I would like to consider is finding the greatest common divisor of two such numbers. A and b are positive integers, so both these numbers are integers and both are positive. And the most interesting part about this greatest common divisor is the answer. So I will give you the answer immediately. It appears that GCD is equal to 3 to the power of GCD of A and B minus 1. So the number of the same form where powers A and B give their GCD to the GCD of the big numbers. So let's try to explain this. Let's try to apply something like Euclidean algorithm to these two numbers. Well, 3 to the power of a minus 1, we need to divide by 3 to the power b minus 1 with the remainder. Well, in order to obtain 3 to the power a, multiply this by 3 to the power of a minus b. Well, of course, we assume that a is greater than b. Otherwise, we would change places of these two numbers. And plus, well, we need to add 3 to the power a minus b and minus 1. And remember the main cause why Euclidean algorithm works. It works because the greatest common divisor of these two is the same as the greatest common divisor of these two. So we can write this down. And we see that instead of the original pair of numbers, now we have another pair of numbers of the same form, some power of number 3 minus 1. But instead of a and b, here we have b, the same as before, and a minus b. Now recall that substituting pair AB by pair B and A minus B is actually one of the forms of Euclidean algorithm on the set, on the ring of integers. Thus, applying Euclidean algorithm to numbers of this form, we actually apply Euclidean algorithm to their powers. See, AB, we change to B and A minus B. This means that after the Euclidean algorithm of the original numbers is finished, we will obtain the greatest common divisor over here in the power of number 3.